Welcome to the deep dive. Today we're looking up way up at the sun. You know, that massive ball of fire that usually just blinds us if we try to look too closely.
Right. Its brilliance hides so much.
Exactly. But what if I told you scientists are now basically making solar eclipses happen? Not here on Earth, but out in space.
Creating them on demand, essentially.
Yeah. Crafting these artificial eclipses to finally get a good look at the sun's biggest mysteries. It's pretty wild stuff. The precision involved is just, well, it's kind of mind-blowing. And the data coming back, it's already changing how we see our star and its effect on us. Now, before we really dive into the nuts and bolts, just a quick heads up. We actually put together a video over on our channel that shows some of the concepts we're talking about today visually.
Oh, that's useful. Seeing the formation flying really helps grasp it.
Totally. So, if you want another perspective after this chat, definitely check that out.
Good idea. And it's worth stressing why this is also important. It's not just cool tech, right? We're trying to answer fundamental questions about the sun's atmosphere, its corona.
Absolutely. Because understanding that directly relates to how the sun affects Earth, our technology, everything. This mission is potentially crucial for protecting our modern way of life.
Okay, so let's unpack that. We're talking about the European Space Agency's Proba-3 mission. And like you said, it's not just one spacecraft.
No, it's two working together.
Two spacecraft achieving something totally new. The first artificial total solar eclipse in orbit. They're not waiting for the moon. They're making their own eclipse.
Precisely.
So you've got the coronagraph spacecraft and the occulter spacecraft, and they fly in this perfect formation, about 150 meters apart.
Which sounds far, but in space terms, keeping that distance stable is the challenge.
Right. And here's the kicker. They maintain that distance, that relative position, down to a single millimeter for hours without someone on Earth constantly steering them.
Yeah, no joystick involved. It's autonomous.
It just sounds... How do they even manage that kind of precision? Millimeter accuracy at 150 meters. It really does push the boundaries. It's a combination of really innovative technologies, think highly accurate laser systems, constantly measuring the distance and alignment between the two.
Like super precise laser rulers.
Kind of, yeah, laser metrology. This feeds data into incredibly sensitive microthrusters. These aren't big engines. They fire thousands of times a second, just tiny nudges.
Wow, thousands of times.
Yeah, constantly correcting, adjusting, keeping everything perfectly lined up. It's less about staying still and more about this continuous, super fine-tuned dance in space.
The dance, I like that.
And the mechanics are quite neat. The occulter spacecraft has this 1.4-meter disk. When it's in exactly the right spot, it blocks the sun's bright face perfectly for the coronagraph.
So it casts a shadow.
Exactly. It casts a tiny 8-centimeter shadow right onto the coronagraph's main instrument, which is called ASPICS. It's like holding your thumb out to block the sun, but, way more precise and engineered.
An 8-centimeter shadow from 150 meters away. Incredible.
It is, and it's worth mentioning, a lot of this tech, the lasers, the control systems, it didn't just appear. It came out of ESA's long-term technology programs, like the General Support Technology Program. Shows the value of that foundational R&D.
Definitely pays off. So ASPICS gets this perfect shadowed view. And you said it's looking at the sun's outer atmosphere, the corona, which brings us to that huge puzzle, right?
Temperature paradox, yep.
Why is the corona, the atmosphere, millions of degrees hotter than the sun's surface below it? It feels backwards, like the air around a fire being hotter than the fire itself.
Exactly. It defies our basic intuition about heat transfer. It's been a major question in solar physics for, well, decades.
So how does ASPICS help crack this?
Its big advantage is getting close. It can study the corona much nearer to the sun's actual surface or limb than most other instruments. And crucially, this artificial eclipse setup dramatically cuts down on stray light.
Stray light, you mean just scattered sunlight?
Precisely. Normally, the sun is so overwhelmingly bright that it scattered light floods detectors, trying to see the much, much fainter corona right next to it. It's like trying to see a firefly next to a searchlight.
Oh, okay.
ASPICS, working with the external occulter disk, has internal shielding and design features baffles, and another internal occulter specifically to minimize this stray light. It means the detector gets a much cleaner signal.
So it can see fainter details.
Exactly. Fainter structures closer to the surface where the heating mechanisms are thought to actually originate. Things like magnetic waves or tiny energy bursts, nanoflares maybe. Getting that clean view right at the edge is key.
Okay, so it's tackling the big temperature mystery. But observing the corona is also vital for understanding things that affect us more directly, isn't it? Like the solar winds.
Absolutely. The solar wind, this constant stream of particles flowing out from the sun, originates in the corona. And then there are the really big events.
CMEs,
Hmm.
coronal mass ejections.
Right. CMEs. These are enormous explosions of plasma and magnetic fields flung out from the corona. They can happen almost daily when the sun is particularly active.
And these are the things that cause auroras, but also problems.
Exactly that. They create beautiful northern and southern lights, but they can also wreak havoc on our technology.
Like we saw fairly recently, right? May 2024.
Yes, that was a significant event. A series of strong CMEs hit Earth, causing noticeable disruptions. We saw impacts on high-frequency radio communications, GPS systems weren't quite as accurate for a time, and there was definite stress on some power grids.
So understanding these things isn't just academic, it's about protecting our infrastructure.
Absolutely. Predicting when a CME is coming, how strong it might be, that's vital for space weather forecasting and giving operators time to, safeguard satellites or power grids.
And Proba-3 isn't just ASPIICS, right? I think you mentioned there are other instruments on board, too.
That's right. While ASPICS and the corona are the main focus, it carries other important instruments. There's DARA and 3DEs.
Okay, what do they do?
So DARA, that's the digital absolute radiometer, measures the sun's total energy output very precisely, what we call total solar irradiance.
Why track that? Does it change much?
It does change slightly, and even small variations over the long term are really important inputs for climate models, understanding Earth's energy budget.
I see. And 3Ds?
3DEs looks closer to home. It's a 3D energetic electron spectrometer. It measures high-energy electrons trapped in Earth's own radiation belts, their direction, their energy.
And why measure those electrons?
Because those energetic particles are a major hazard for satellites orbiting within those belts. They can damage electronics, degrade solar panels. Understanding how they behave helps us design more robust spacecraft and maybe even predict periods of higher risk.
Gotcha. So it's providing a more complete picture of the Sun-Earth connection.
Exactly. Complementary data.
Okay, let's circle back to the main event, the artificial eclipses. How does this capability really stack up against natural eclipses, the ones we see from Earth? What's the real game changer here?
Oh, the difference is enormous for scientists.
Yeah.
Think about natural eclipses. They're rare, right? Maybe 1 or 2 total eclipses somewhere on Earth each year.
And you have to be in exactly the right spot.
Exactly. And even then, totality, the part where the corona is visible, only lasts for a few minutes, max.
Right, it's over so quickly.
About the 3, it can create its eclipse once every orbit. That's about every 19.6 hours.
Every day, basically.
Pretty much. And it's not just for minutes. It can hold that artificial eclipse stable for up to 6 hours per orbit.
6 hours compared to a few minutes.
Yeah. Imagine the difference. Trying to study something complex and dynamic, would you prefer scattered snapshots for a few minutes a year or continuous high-res video for 6 hours every day?
No contest, really.
And the quality is there, too. The images are comparable to what you get during a natural eclipse, critically with much less stray light. So you get a clearer view, especially of that really important inner corona region. That sustained, long-duration, high-quality observation time is the revolutionary part.
It's like having a permanent, high-definition eclipse observatory in space.
That's a good way to put it. 2 spacecraft acting as one giant coronagraph.
So with all this amazing data flowing back, what's the next step? It's not just about collecting images. It's about improving our understanding, our models, right? Particularly space weather models.
And absolutely. That's a huge part of the why. Current coronagraphs, even space-based ones, just don't give us enough detail, especially close to the sun, to really feed and validate the sophisticated computer models we're developing.
They're data starved, in a way.
You could say that, especially for that critical region near the solar surface. Proba-3 observing right down to the edge, like during a natural eclipse but for hours on end, that's the data injection these models need.
How does that help refine them?
Well, modelers can take the Proba-3 observations, actual images and data of the inner corona, and compare them directly to their simulations. They can see where their model matches reality and where it doesn't.
And then tweak the model.
Exactly. Adjust the parameters. The physics inputs things like magnetic field strength, plasma density, until the simulation looks like the real thing Proba-3 is seeing. Take KU Leuven's coconut model, for instance. It's part of ESA's Virtual Space Weather Modeling Center.
Okay.
It simulates the corona. With Proba-3 data, they can fine-tune Coconut to be much more realistic, especially in how it models energy transport and the very beginnings of CMEs near the sun's surface. That was almost impossible before.
So connecting the dots for everyone listening.
Mm-hmm.
Better models mean better predictions.
That's the goal. These refined solar models, combined with models of how CMEs travel through space and interact with Earth's magnetic field, give us a much clearer, more comprehensive picture.
Which helps us prepare.
Yes, better warnings for potentially disruptive space weather events. It helps airlines redirect planes, satellite operators take precautions, power grid managers stabilize their systems. It benefits citizens and industry directly.
That makes sense. And this whole complex mission, it wasn't built by just one country, was it?
Oh, no, not at all. It's a major international effort.
Yeah.
Led by ESA, the European Space Agency, but the prime contractor managing the build was Sener in Spain. And then you had contributions from, I think, over 29 companies across 14 different countries.
Wow.
Yeah, key players like GMV and Airbus in Spain, Redwire and Spacebel in Belgium, and many others. And it launched relatively recently, December 2024, from India on an Indian PSLV rocket. Truly a global collaboration.
It really is an incredible story. Proba-3 is such a testament to, well, human ingenuity, isn't it? Just drive to understand the universe, even the parts that are hard to look at.
It really is.
Pushing technology to its limits to answer fundamental questions. That blend of precision engineering and deep scientific curiosity, peeking behind the sun's glare.
And it highlights how vital these kinds of missions are, not just for pure science, which is fascinating in itself, but for tangible benefits back here on Earth.
Yeah, protecting our technology, understanding our star's influence.
Exactly. The better we understand the sun, the better prepared we are. It just reinforces that sense that there's always more to learn, more to discover, even about something we see every day.
So true. Okay, here's a final thought then for you listening. If we can achieve this kind of precision formation flying to create an artificial eclipse, what else could we do with it?
Interesting question.
Imagine applying that kind of coordinated multi-spacecraft approach to other hard-to-observe phenomena. Maybe studying exoplanet atmospheres by having one spacecraft block the starlight, or mapping gravitational fields with incredible accuracy. What new cosmic windows could this kind of tech open up?
The possibilities are vast.
Definitely something to think about. And remember, if you want to see some of this in action, check out that video on our channel. For now, thanks for joining us on this deep dive.